properties solid. Fine. So let's begin with this. See, to understand this lesson, we have to know basic definitions and basic terms. So for understanding that, let us take an example. I have taken this wire. Let this wire be any random wire, a steel wire, for example. So it has its original length. It has some certain length of it. Let's say that length is L. Now what I've done, I have applied a block of mass M at its free end. So can you tell me what would be the force at its free end? Any force will act in the downwards direction. Are you able to recall? Yes, are you there? Am I audible? Fania? Hello? Hello?
Ma'am,
Yes. Yes.
sorry, ma'am, I was having some technical
Okay,
error.
okay. Yes,
Could you
network is
please
working.
repeat? Like,
Yes, yes, I was asking you from where did you hear? Till where did you hear? Because I wasn't aware that my voice is not reaching to you.
actually, we're having technical error, right? So I joined
Yes.
again. So,
Okay, so shall I repeat it from the beginning? Will it be fine to you?
yes, please, ma'am.
No, okay, fine. See, I was telling you that we have this unit which is properties of bulk matter. It comprises of two chapters. The first lesson which we have is mechanical properties of solids. And the next chapter we'll be dealing with mechanical properties of fluids. So today we have begun with mechanical properties of solids. So to understand this lesson, we have to know few basic definitions. To understand those definitions, I have taken an example in which I have suspended a steel wire. So the original length of this wire is L. The original length, the wire must be having certain length of it. So I have taken that length as L. Now what I have done, I have suspended a block of mass M at its free end. So I was asking you, can you tell me what would be the force acting over here?
Ma'am, at its free end, right?
Yes, at its free end. Any downward force acting, if you are able to recall. M
Sorry.
is the mass. In the downwards direction, mg will act. Yes? Now are you able to recall?
Yes,
Gravitational force will act. F
yes.
is equal to mg. Now see what happens. Because of this block of mass m, this force has been generated mg. Now what it is doing, it is pulling the atoms. So the inter atoms interatomic molecules will move away from each other. So can you tell me, will its length increase or decrease?
Increase.
Increase. Definitely it would increase. So let's say by some certain this much amount delta L, its length has been increased. Now what I have observed, I have removed this mass. Now what I have observed is that after removing this mass, the wire's length is again back to L, and L was its original length. So these kind of forces which produce change in the configuration. The configuration can be anything. It can be change in shape, it can be change in volume, it can be change in length. So in this example, what we have seen, on application of this deforming force, there was a change in length. Yes, there was a change in length, right?
Yes, ma'am.
So these types of forces are known as deforming force. These types of forces are known as deforming forces. These deforming force produce change in configuration. And this property of this property of solid to regain its exact original length, like in this case we have seen that this wire was able to regain its length back. There was some extension produced in the wire. So this extension has vanished now after the removal of this load. So this property, this tendency of any solid to regain its shape and size after the removal of these deforming forces, that property is known as elastic property. So the tendency of the object, or the property by which the solid object is able to regain its length, that is known as elastic property, and the phenomena is known as elasticity. Clear?
Yes, ma'am. Ma'am,
Yes.
actually, I always had this doubt. The delta.
Mhm.
What is exactly delta?
Delta means change.
Change, right? Like,
Change, yes. For example, I'll tell you. Let's say this original length is 6 meters. Now it has increased. This wire has increased to 10 meters. What is the change in length?
4 meters.
4 meters. So that is delta L. That change in length, what we are getting, that is known as change in length.
Okay.
Fine, means change. That means final minus initial. That would be the change. All right.
Yes, ma'am.
See, now elastic bodies are also not of only single type. If the body is able to regain its exact shape, means if the length was 6 meters, after regaining this 10 meter, once I have removed this block, then its length is again 6 meters. It means exact length has been recovered. So those types of bodies which are able to regain their exact original shape and size immediately after the removal of these deforming forces, that type of body is known as perfectly elastic body. For example, quartz we have in the example of it, phosphor, bronze is there. These are examples of nearly perfect elastic bodies. No body in nature is actually perfectly elastic. Now see, if the body is not able to regain its exact length, for example, 6 meter was its original length, it has regained to 10 meter. Now it has compressed back to, let's say, 7 meters. So 7 meters was not its original length. Its original length was 6 meters. So these kind of objects which are not able, a body which does not have any tendency at all to regain its original shape and size, that body is known as perfectly inelastic body. Perfectly inelastic body. Or this phenomena is also called plasticity, and the types of perfectly inelastic bodies are known as plastic bodies. So one we have perfectly elastic, where the body is able to regain its length, exact original length, not length or whatever is the configuration, size, shape, any, be it any. And if the body is not able, then that is known as perfectly inelastic. For example, in perfectly inelastic, you can have the example of paraffin wax, or you can have the example of wet clay. Once you apply force on clay, the clay gets deformed. It has certain shape which you have molded it to. Now, once you have removed it, once you're not touching it, what will happen? The clay won't go into its original position and shape. Yes, it will remain deformed, or it will have the tendency to regain, but not exactly the same. So that those types of bodies are known as perfectly inelastic bodies. Clear?
Yes, ma'am. I wanted to ask
Yes.
examples of perfectly elastic bodies again, please.
Yes, yes. I have written quartz and phosphor bronze. Don't worry, I have the definitions written it for you. Fine, you
Uh,
can note these definitions right now. And if
okay.
you wish to note the above portion, just let me know. I'll scroll it up.
Ma'am, I have copied that.
Just note these definitions. Fine. No.
Yes. Um, done, ma'am.
Done?
Yes.
See, so that was about the basic definitions of elastic properties. Elastic body, perfectly elastic, perfectly inelastic, and the deforming forces. See, now on the basis of these deforming forces, we have various types of deformations produced because of the deforming force. So see the first one. There can be a change in length produced because of the respective deforming force. This example we have seen just now, that wire example, the length was increased. Why? Because of the deforming force that has been applied. The gravitational force acted as the deforming force. So there can be a change in length. If the length increases, for example, this yellow wire is the original wire, and I've applied a force in the upwards direction. So the length would increase. That is known as tension. And if the length decreases somehow, like for example, if I've applied the force in the downwards direction, that would decrease its length, and that is known as compression. So this is the first type of deformation. It means the deforming force can produce change. See, although a solid can be deformed in many ways, there are three basic types of deformation. And all the other types of deformations are a combination of these. So the deforming force causes a change in length of the object. The second one is that the deforming force also produces change in volume. Fine, the volume may decrease or increase, so will be change in volume. The third one is there, change in shape. It means the deforming force can produce change in the shape of the body. Clear? Yes, Panya, is the network issue resolved? Are you able to hear me?
Yes, ma'am. I'm really very sorry for the disturb.
No, no, it's so fine. Fine. There must be technical issues, I understand. See,
Yes.
did you hear anything from this portion?
Ma'am, types of solid deformations?
Yes?
No, ma'am.
Okay, I'll repeat it. Don't worry, I'll repeat it for you. See, I was saying that the deforming force produces various types of deformations. Not only in length that we have seen, it produces change in length as well as volume as well as shape. So if the deforming force increases the object's length, for example, this wire, if I apply a force in the upwards direction, that would increase its length. That is known as tension. And somehow, if it decreases its length because of the application of the downward force, then that is known as compression. So see, I was telling you that the deforming force produces not only, see, one thing, remember that although a solid can be deformed in many ways, there are basic three types of deformations, and all the other types of deformations are combination of these. So the deforming force causes a change in length, it causes a change in volume, and it also can cause change in shape. Understood?
Yes, ma'am.
Okay, fine. See, two quantities are there. Stress and strain are two quantities used to describe the nature of the applied force and resulting deformation. So let's learn about stress first.
Ma'am,
Yes,
can I copy down last
yes,
slide?
yes, 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 you can.
Yes. Sorry. Thank you, ma'am.
Done? Fine.
Yes, ma'am.
Okay, so let's discuss what is stress. See, when an external force is applied to a body, that changes its size or shape that we have been discussing. For example, this force F have been applied in the downwards direction. So there is an internal restoring force developed in the body. So this internal restoring force acting per unit area of the body, that quantity is known as stress. Fine. So
Yes.
the internal restoring force acting per unit area of the deformed body is called stress. This means if I take 1 meter square area, and whatever force, deforming force has been acting in this 1 meter square area, that is known as stress. Clear? So deforming force is equal to the restoring force. This deforming force is equal to the restoring force. So if we wish to write the formula for stress, this is known as the internal restoring force that has developed in the body per unit area. Or you can say this is the restoring force, or you can say the external deforming force acting on the area of the object. This is known as stress. And stress is a scalar quantity. It means it has no direction. Now, can you guess its SI unit? If stress is force divided by area, what should be its SI unit? What is the SI unit of force? SI unit of force, do you remember?
Ma'am,
Yes,
am I audible?
yes, yes, you're audible now.
Ma'am, SI unit of what did you ask?
Yes, sorry, can you repeat?
S unit of what did you ask?
Force, force. SI unit of force. Do you remember the SI unit of force? You must have done that in laws of motion.
Ma'am, Newton.
Newton, exactly. And for area, it's
Meter.
meter square.
Square.
Meter square, yes. For length, it's meter. Had it been length, that is meter. For area, it's meter square. And also, I'll tell you that 1 Newton per meter square is equal to 1 Pascal. So you can write the SI unit of stress as Newton per meter square as well as Pascals. Clear?
Yes, ma'am.
See, let's write the dimensional formula for it. The formula is force by area. The dimensional formula for force is mLT to the power minus 2. Minus 2. And do you remember the dimensional formula for area?
No, ma'am.
See, since the SI unit is meter square, it means area is L square. So that is L to the power 2 only. Because it's meter square. SI unit is meter square. Area is basically length into breadth. We write it this way. So the dimensional formula would be m L to the power minus 1 T to the power minus 2. Fine. Just note this portion. Then we'll discuss types of stress. And if you have any doubt in between, you can ask me.
Ma'am, dimensional formula. Actually, I'm hearing this for the first time.
You're hearing it for the first time. You have not done dimensional analysis, error analysis.
No, ma'am.
Okay, it might have been deleted then. Okay, I'll tell you. See, these are basic mass, length, and time are the basic fundamental quantities which we use to create the dimensional formula. For example, if for velocity, the formula for velocity is distance upon time. So distance is represented by L, length. So the dimensional formula for velocity would be L divided by T. And if you transport it, T on the numerator side, that would give you T to the power minus 1. Understood? This is for velocity. So similarly, by using the formulas, we have like for force, if you wish to calculate, you can write it mass into acceleration. And acceleration, how can you find it? Acceleration is velocity by time. Velocity is L T to the power minus 1 divided by T. That would give you L T to the power minus 2. Yes?
Yes,
And if
ma'am.
you multiply it with mass, means mLT to the power minus 2. That is ma. That would give you force. So force is mLT to the power minus 2. And for area, since area is L square, meter square, that's why it's L to the power 2. It's not very important. It's just for your knowledge. I've written it down.
M represents what, ma'am?
Mass. M
Mass.
is mass, L is length, T is time. These are the basic fundamental quantities. We have other as well. For current, we have ampere. So we have other as well. But for now, remember M is for mass, L is for length, and T is for time. So if you have to derive any other formula, like for example, we wanted to find out for force. If we have to find out for force, then see, we know the formula for force. Force is mass into acceleration. So we can find out the formula for acceleration using this velocity by time. And if we want to calculate it for velocity, you can write by distance upon time. Now see, distance and time are the basic quantities. You don't need any other quantity to describe length and time. So you can write L by T. That would give you velocity. L T to the power minus 1. If you divide it further by time, that would give you acceleration. L T to the power minus 2. If you multiply this by mass, that will give you mLT to the power minus 2, which is force. That's what we were requiring. Understood?
Yes, ma'am.
Fine. Just note this.
completed, ma'am.
Done?
Yes, ma'am.
Okay, fine. Now see, let's see the various types of stresses which we have. See, the stress developed in a body depends on how the external forces are applied over it. So on the basis of it, we have the first stress that is known as the normal stress, or the other name for normal stress is the longitudinal stress. See, if the deforming force which we have been referring continuously, the force that produces change in the configuration, if that force is applied normally to the surface, like for example, I have taken this block of mass m and I've applied a force in the upwards direction, it means it is making an angle of 90 degree. It is making an angle of 90 degree to the surface. Then the force per unit area developed is would give me normal stress. Or you can have this example of the wire again. If the force is acting in downwards direction, then that force is making an angle of 90 degree with the cross section area. If A is the area of this cross section, then the force per unit area would give me normal stress. And how it differs it from the other types of stress? By being parallel to the surface. Fine. If the deforming force is applied normally, perpendicularly to the surface of body, then that force per unit area developed is known as longitudinal stress, or you can say normal stress. So the formula for longitudinal stress is equal to force, the perpendicular force that has been acting per unit area. Clear? Now see, if this deforming force increases the length, like in the wire example which we are considering, the length was increased by we have taken that delta L is the extension produced. So if there's an increase in length of the body, then that stress is known as tensile stress. And if there is a decrease in length of the body, then that respective stress is known as compressive stress. So tensile stress and compressive stress are the types of normal stress only. Normal stress has been classified into tensile stress as well as compressive stress. Again, the SI unit would remain the same, Newton per meter square or pascals. Clear?
Ma'am,
Yes?
the force applied would be parallel to the mass of the body.
No, perpendicularly. Normal means perpendicular.
It would be perpendicular to the mass of the body.
Yes, to the surface of the body.
Mm, okay.
Like this is the upper surface, then the force is making an angle of 90 degree with this surface.
Okay. Done, ma'am.
All right, see the next type of stress which we have is known as tangential stress. Now here the force applied is parallel. If the deforming force is applied parallel to the surface of the body, then that force per unit area is known as tangential stress, not normal stress. This is known as tangential stress. And this brings out change in shape. Now let's see how it brings change in shape. This rectangular portion, yellow line, which you see, this is the original shape. Now I have applied a force, this force parallel to the surface. See, it's parallel to the surface. Perpendicular was this, like this.
Hmm.
It has been applied parallel to the surface. Since it has been applied on the upper layers, won't it shift the upper layers a bit far and the lower layers will remain intact? For example, you can apply this in your daily life as well. If you have a thick book, then if you apply force in the upwards direction, in the parallel direction on the upper pages, then what will happen? The initial pages of the book will shift further while the lower pages will remain intact. Yes, it would tilt the book. So that type of deforming force produced per unit area is known as tangential stress. Clear to you? So tangential stress is equal to, now can you tell me what would be tangential stress if F is the deforming force applied and A is the area of this upper layer?
From F by A.
F pi, yes, right, F pi, because it's force acting per unit area. And again, the SI unit would remain the same, Newton per meter square or Pascal.
Okay.
Yeah.
Yes, ma'am.
See, we have a last type of stress as well. That let me tell you.
Ma'am,
Hmm. Yes.
I'll copy once.
Yes.
I'll copy the earlier
Yes.
notes.
Yes. Yeah, I'll give you time. This is a very
Okay.
small one. That's why.
Okay.
See, I have a spherical body. Now I've applied forces perpendicularly to the surface of this. Because if you apply a force on the sphere, like this, making an angle of 90 degrees. So all these forces, F are the deforming forces. Now it will change its configuration, means it would compress it. So now the force acting per unit area, that would give me volumetric stress. That is force acting per unit area. So now you can copy down. And when you are done, let me know, I'll scroll the page down.
Okay, ma'am. Done, ma'am. Ma'am,
Yes,
what would be the definition of volumetric stress again?
volumetric stress is same. The force applied per unit area. Here the force is actually perpendicular, which we have discussed in this case only, normal stress. The deforming force is applied. The definition would be if the deforming force, is applied perpendicularly on a body which changes its shape or volume, actually changes its volume. Then that deforming force produced per unit area is volumetric stress.
So, ma'am, here the direction doesn't matter, right?
Yes?
Here the direction doesn't matter. In which direction we are applying the force?
No, the force should be perpendicular.
Okay.
Perpendicular to the surface.
So any like any we can from any side we can apply
Yes,
the
yes,
direction.
yes. That direction doesn't matter because it's a spherical object we have taken. So for spherical object, if you apply the force in any direction perpendicularly, that won't affect it. You can take it from any direction. And even for the previous cases as well, if you apply the force from here in this parallel direction, then also the force per unit area would give you the tangential stress. So direction doesn't matter. Yes.
Completed, ma'am?
Yes. Completed?
Yes, ma'am.
Okay. See the other quantity which I was talking to you, which is based on the nature of the applied force and the deformation produced, is known as strain. So let's see what is strain. So that change produced in the body or whatever deformation has been produced, that is known as strain. The change in size or shape of a body due to the deforming force is called strain. We say that the body is strained due to stress developed. So strain is basically the ratio of the change in the dimension. Dimension means the change in length, the change in volume, the change in shape. It can be any change, the deformation which we have seen. So strain is ratio of the change in dimension to the original dimension. This means that if this is a wire of length L and the deforming force produced in the downward direction is F, and it has extended this by this much amount, and we are taking it as delta L, and F is the force. Now see this change in length, this change that we are able to observe divided by its original length that was taken initially, that would give us the physical quantity that is known as strain. Now can you tell me what should be its SI unit? Yes?
Sorry, ma'am.
Can you tell me what is the SI unit of strain? See, strain is the ratio of two similar quantities. Means the similar dimension is there on the numerator side and the similar dimension is there in the denominator side. Then its SI unit should be?
M by M, so it will be 1.
No, see it won't be 1. It won't have a unit. It would be a pure number because it's the ratio of two similar quantities. Like for example, let's say the dimension here is length. Let's consider this example only. Fine. So change in length. The dimension here would be change in length by the original length. So this would have no unit. So it would be unitless. So one that what you were saying, one is a constant number. One is not a unit. Yes. So that's why it would be unitless and it would be dimensionless. Dimensionless how? If length is taken or whatever is the dimension taken in the numerator or in the denominator, both are same. So that's why how we'll get a dimensionless quantity. Understood what is strain? Now see, since deforming force can produce various types of deformations like change in length, change in volume, change in shape, the strain is also of three types. So first one is longitudinal strain. Let's discuss the strain and I'll give you time to note them. See, if the deforming force produces a change in length, for example, that example we have been discussing so far, the wire example. The length of the wire is L. This is a wire of length L. So L is the original length. Now, because of application of the deforming forces, deformation will be produced, means length has been changed. So this change in length, again I'm representing it by delta L. So L, this much portion is the initial original length, delta L is the change in length. Can you guess what should be the formula for longitudinal strain? Strain is change in dimension divided by the original dimension. So longitudinal strain should be?
Ma'am, it would be again change in dimension by original dimension.
Original dimension, exactly. And the dimension that is changing in this case is the length. So this would be change in length by original length. And change in length is being represented by delta L, and the original length has been represented by L. So in this case, what we have observed that this deforming force caused a change in that parameter. And what is that parameter? Length alone. So if the deforming force produces change in length alone, then that strain we get is called longitudinal strain. See, what is the SI unit of length? Meter. And what is the SI unit of length again? Meter. So that would cancel. That's how we were getting unitless. So again, it would be unitless. So that is known as longitudinal strain. Here, the deforming force, when the deforming force produced a change in length alone. Now we have the second type of strain, that is known as the volumetric strain. See, I have taken a sphere. Again, I have taken a sphere. Now see, I have let the volume be V. This is the original volume of the sphere I have taken. Now I have applied these deforming forces from all the directions. Now this would definitely compress the sphere. Its volume will also get changed. Let us say that the volume of this dotted, this new sphere is V dash. V dash is the new volume. So are you able to observe this change from this yellow periphery to the center?
Yes, ma'am.
So this change, let us say this change is delta. Delta V is the change in volume. So now can you tell me what is the formula for volumetric strain? The formula for strain is change in dimension by original dimension. And what is the dimension that is changing over here?
Over here is volume.
Volume changing. So it would be change in volume by original volume. And what is the change in volume? Delta V means whatever change has been taken. Like for example, if 5 meter cube was the original volume, now it has compressed to 2 meter cube. So what is the change in volume? 3 meter cube. So that's how we get volumetric strain. Change in volume by the original volume. And again, volume divided by volume would be unitless. Like one that you were saying, it won't have any units. So this is known as volumetric strain. What is volumetric strain? If the deforming force produce a change in volume alone. If the deforming force produce change in length, then that is known as longitudinal strain. And if the deforming force produce change in volume, then the strain produced is known as volumetric strain. Now we have last type of strain. Let's discuss this also.
Mama,
See, I have applied a deforming force in this direction. Now again, we have discussed this previously as well, that this would rotate, shift it, tilt the object that we have. Now see, let us say this angle is theta. By some theta, it has been shifted. So this, I am naming this triangle. This triangle we are getting A, B, C. So let's say this original length we have is L. Again, L is the original length, and it has been shifted. That it means the initial point was B. Now the final point is C of this. Now this change is represented by delta L. So I'm drawing this triangle here separately for you. A, B, C. This is theta. This is L. AB is L, and BC is delta L. So in this triangle, can you tell me in triangle ABC, how do we take tan theta? How is tan theta calculated? It's perpendicular
by base.
by base. Yes, perpendicular by base. So perpendicular is the opposite side to the theta, making an angle of 90 degrees. So here the perpendicular is BC, and the base over here is the adjacent angle to the theta, that is AB. So tan theta would be equal to, what is BC? What have we taken BC?
Delta L.
Delta L. And what have we taken AB?
L.
L. See, when the angle is very small, like in this case, the angle is not very much. So tan theta is approximately equal to theta. So theta would be equal to delta L divided by L. And this that we are getting, this theta that we are getting, this is our shearing strain. Understood?
Ma'am,
Yes.
tan theta is
Perpendicular upon base.
no, ma'am.
This
Yeah,
this
ma'am.
portion.
Yeah.
See, when the angle is not very large, then tan theta is approximately equal to theta. You can take it as theta. Fine. If the angle is not very large.
Okay.
Because obviously, if you even take that example of the book which I was telling you, it would shift a bit. This won't be much. So that's why you can equate it to theta. So just start writing this down. And when you're done, let me know. I'll scroll it down. So and if you have any doubts in between, you can ask me.
Okay, ma'am. Done, ma'am. Done, ma'am.